Hello everyone. So another skills video there on functions. Remember in the other video we talked about what a domain was. So that's all your starting values, that's all your x values, right? And that produced a range, which was all your y values, which was in the form of f of x, let's say, or g of x, or z of x. We talked about types of functions. So if it ends in too many, then it is not a function, because a function is a very specific definition. A function is a special mapping whereby each and every element within the domain maps to exactly one element in the range. And then we did some examples of them. So only one-to-ones are functions and only many-to-ones are functions. Now we're going to deal with composite functions. So what is a composite function? Well, you've been dealing with composite functions all the time. X plus 1 all cubed is a composite function. You start off with x plus 1, that's a function, and then you cube it. So a composite function is just a function within a function, right? Inception, a dream within a dream. How do you actually describe that though? Well, let's see. If we had f of x is x plus 1 and g of x is x cubed, you could describe the composite function as being g f of x. Why? Why can you do that? Well, like I did here, you started with a function on the inside, and then you went outside to cube it, right? So that's the same logic here. What I'm going to do is I'm going to look at this as always going inside out. You know, just as a bit of a prerequisite, that f of pineapples is the same as pineapples plus 1, because whatever's in that bracket replaces the x. F takes whatever's in that bracket and then adds 1 to it, right? So if I had f of y cubed plus y, well, remember that's going to replace whatever that x is, and then f takes that and then just adds 1s to it. So that's going to produce y cubed plus y plus 1. Similarly, g takes whatever's in there and cubes it, right? So let's apply the same logic here with g f of x. If I've got g, remember I'm always working inside out, f of x was x plus 1, keeping that g on the outside. Now g of whatever is always whatever cubed. So g of x plus 1 must be x plus 1 all cubed, see? And there's your composite function. How does the theory work though? Remember we used mappings last time to kind of describe what's going on, and remember you're not going to actually use mappings ever. It's just a way for you to understand the theory of what's going on. So you don't need to be drawing these bubbles every time, but it's just helpful to know what's going on. So this is advanced stuff, but everyone should be able to grasp hold of this idea. Let's say we wanted to do gf of x again, but in like a general term. So actually let's stick with our example, yeah. So when f of x is x plus 1 and g of x is x cubed, and let's say in this situation f's domain is x is all the real values and g's domain is also x is all the real values. So both can take all the real values. Actually, yeah, okay, let's do that. So, starting with the domain of f then, because remember we always work inside out, f's domain is our x values, which x is all the reals, okay? So domain of f is x is all the reals. F takes all those values then and adds 1 to them. So in here I get my x plus 1. So my range of f becomes f of x equals x plus 1, where f of x, so let's think about it, if x is all real numbers, and then I add 1 to all those real numbers, then my range is going to be all real numbers. Let's think about it. X plus 1 is that graph. If all the x values are allowed, then all the y values will be allowed, so therefore f of x can be any real number. But then g has its role to play. G now takes everything from this bubble, doesn't it? And cubes it. So, in order for G to take something that the other function has left off, then if we look at it like a relay, like a factory, you can't build anything from a factory if you don't have the right parts. Likewise, you could look at this like a post office. So someone has some post, they send it to the post office, it gets processed by the people in the post office, and then the post person then takes it and delivers it, right? So the post person can't deliver anything if it's not there. All they can deliver is what's in that post office to start with. So therefore, the domain for G has become the range of F. So the domain for G is f of x is all real numbers, right? G then takes that value and then cubes everything, so whatever cubed, and then produces our range of G, which is G f of x. And again, cubed, anything cubed, as G takes all real numbers, its range will have all real numbers as well, and therefore G of f of x will take all real numbers. So what I'm saying is, when you have a composite function, the domain, the range of your first function becomes the domain for your second function, and it would keep going from there. Let's test this out then. So I've got the functions f and g are defined such that f of x equals 3x plus 2, where x is all the reals, and g of x equals x squared plus 4, where x is all the reals. Find f of g 1. Okay, like I say, we always work inside out, and we're saying that f of x is 3x plus 2, domain all the reals, and g of x is x squared plus 4, domain all the reals. Okay, so fg of 1 is f, remember always leave it on the outside, and now we've got g of 1 working inside out. G of 1 is 1 squared, that's 1 plus 4, so that's f of 5, and f of 5, now I can put that in here. That does match the domain, so 5 is okay, 5 is part of all the real numbers, so 3 times 5 plus 2 is 17. G of f of 2 then, so the next bit, this bit, let's try that again, working inside out. So leave the g on the outside, big square brackets, f of 2. 2 is a real number, so that's fine. 3 times 2 plus 2, so that's g of 6 plus 2 is 8. And now I can go to my g, and g has domain all reals, and therefore I can put, like 8 is a real number, so that's fine. And I can put that in here. So 8 squared is 64, plus 4 is 68. And there we go. Part B. Let's try part B. Right, a bit more difficult this time. State fg of x and its domain and range, and state g f of x and state its domain and range. So fg of x is f of g, and g is x squared plus 4. So whatever's in that bracket replaces my x in here. So this is 3 x squared plus 4 plus 2. So that's 3x squared plus 12 plus 2 is plus 14. Like we did on our mapping, the domain of our fg, domain for fg, so what values can it start with? Well, it starts with all the reals because g starts with all the reals. And let's think about what happens then. G then takes it, but let's think about g. So this is a complicated example, but if you understand what's happening, g takes all those x values to start with, and so therefore we need to know the range of g. Well, g is x squared plus 4. X squared plus 4 looks like this. Its lowest point is 4, isn't it? So if x is all the real numbers, everything here is included, but the lowest possible point, the range, is everything bigger than or equal to 4, isn't it? Bigger than or equal to 4, because g can't get less than 4. So that means that the range of g of x is greater than or equal to 4. Therefore, the domain for f, then, when it takes that on, is x greater than or equal to 4. We don't have g's in there anymore and stuff like that. We're saying x is all the real numbers greater than or equal to 4. And then f takes that value then. So the range of fg of x, if x is greater than or equal to 4, f takes it. All f has to work with is numbers 4 and bigger. So 3 times 4 is 12. Plus 2 is 14, so therefore this thing must be bigger than or equal to 14. That is a bit more advanced. I hope you understand what's going on there. We can do the same again, and let's see if we understand that. So, whoops. So let's try gf of x. So, gf of x, again, leave the g on the outside. F of x is 3x plus 2. Now we can g it, and g says square everything and add 4. So 3x plus 2 squared plus 4. That's 9x squared plus 12x plus 4 plus 4. So that's 9x squared plus 12x plus 8. Domain and range then. So the domain starts off as being for f, x greater than or equal to the real x is part of the real numbers, sorry. G takes it, sorry, f takes it, and as f is our 3x plus 2, which looks something like that, it takes all the real numbers, x can be any number, and therefore f of x can be any real number. So the range is f of x is all real numbers, which becomes the domain for g when g takes over. So g has all real numbers, and therefore that takes that on, and as it takes on all the real numbers, which is exactly the same as what we had before, we know that g f of x then must be greater than or equal to 4. I hope that makes sense, how you're moving between these things. F squared, let's think about, oops. Let's think about f squared. So this is part C now. So part C. Remember to pause the tape if you need to. Let's have a look. So part C, f squared of x. That means perform f twice. So f of x. So again, we got f on the outside. F of x is 3x plus 2. We're going to f it, so 3x plus 2 plus 2, because it says 3 times whatever's in there, and then add 2 to it. So that's 9x plus 6 plus 2, so 9x plus 8. Again, what did we start with? Well, we started with a domain of x is all the reals, and then the range, f of x gives you a range of f of x is all the reals as well, because it can be infinite, like that graph we did earlier. So there's 3x plus 2. If all the x's are allowed, then all of the f of x's are allowed. And that then becomes the domain for g, for f again, sorry, because it's happening again. So this one, essentially it just loses its f or its g. It's just, whenever you've got a domain, it should always have x's in it, not f's or g's. Only ranges should have f's or g's in it, okay? So the range now is going to be f of x is all the reals again, because all f has to work with is all the real numbers, and that's what it had before. So there we go. Okay, composite functions and inverses, let's consider this function here then. When f of x equals x squared. So when f of x equals x squared, that looks something like this, doesn't it? That's x squared. So think about these numbers. Let's say we started off with the domain for f of x. So the domain of f is all these numbers here. X is all the real numbers, isn't it? X can be any number along here. When we square them, what do we get? Well, we get 0 goes to 0 when f happens to them. Minus 1 and 1 goes to 1. We've seen this before. To 4. And x goes to x squared, right? And so would minus x. Okay. So, f of x equals x squared. There we go. We have a many to one function, don't we? But what was if we wanted to go backwards? And that's what an inverse is about. If we wanted to go backwards, so the inverse means do the opposite of what you did in the first place. So here we had a domain of f, and here we had a range, which was f of x, right? And remember, our domain was x is all the reals then, and our range was f of x. Well, y can only be bigger or equal to 0, can't it? It doesn't fall. The graph doesn't fall below the y-axis. If I want to go backwards, though, this links with composite functions, because now I'm going to start with my domain as being my numbers on the right here. Yeah, so 0, 1, 4, x squared. And for my range, if I'm going to do the opposite of squaring it, then I'm going to square root it, yeah? So I would plus or minus square root it. So 0 would go to 0 again. Our 1, though, would go to 1 and minus 1. And 4 would go to 2 and minus 2. And x squared would go to x and minus x. What's the problem here? Well, there's a huge problem. Because, so again, if I've got the domain for the inverse, f to the minus 1, it is x is greater than equal to 0, because remember, for our composite functions, we take the domain, the range of the old one, and make it our domain, right? Because in a sense, this is what we're doing. I could draw it another way. We have our 0, 1, minus 1, 1, minus 2, 2, x, yeah? We apply f to it, and then we get all of our stuff, which we had before. That shouldn't be it. Yep, that's just x, and minus x. So we applied f to it. Right? And that produced all of our x squared stuff, right? And then we apply the inverse of it, f to the minus 1. So we had a domain of f, that produced a range, that becomes therefore the domain of f to the minus 1. F to the minus 1 happens to it, and that's what this graph is here. So bang, 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 bang. The problem, do you see, is that this is a one to many, and therefore it is not a function, okay? So graphs only have inverses, functions only have inverses if, notice this is a many to one produced a one to many operation which is not a function. And the reason for that is because, well, you can see it graphically. If you sketch the graph of plus or minus square root of x squared, it will look like this. And this, as we know, this is a many x to 1y. This is a 1x to 2y's, which is a one to many, which is not a function. Notice when you draw inverses, this is a really important point, when you draw inverses, it is a reflection in the line y equals x. Reflection in y equals x. This thing has been tilted on its side. it's being reflected in that line y equals x here. A mirror's been put on it, and it's produced a one-to-many, which is not a function. So, in conclusion, only one-to-ones have an inverse function because of that movement, so that reflection in the axis. So if I had y equals x squared here, or f of x equals x squared here, but I restricted the domain to being greater than or equal to 0, when I reflect it in that line, all it would produce is that curve there. My f of x equals the square root of x, right? Not plus or minus in this case, because in order to have an inverse, it needs to be a one-to-one. So when you get asked, why doesn't this thing have an inverse? You say, well, because it's not one-to-one. One-to-one have inverses. Otherwise, they don't, okay? And they must start off as functions in order to have inverses as well. So, the big conclusion is that in general, imagine it. So, if you take x, so you do something to x, that gives you f of x, and then you inverse it again, you do the opposite, what are you left with? You're left with x again, aren't you? So, if you take x, you do f to it, you get f of x, and then you do the inverse again, back to it, you get x. So a key property is that f to the minus 1 of x is the same as x, and also f to the minus 1 f of x equals x. So if I go backwards and then step forwards again, then I'm back where I started with, okay? I'm back where I started. This is the most key message and bit of theory that we need to learn.